Good morning. My name is Kavitha M and I work as an assistant professor in the Department of Civil Engineering, Rajagiri School of Engineering and Technology. Today, I will be discussing specific energy and specific energy curve, a topic from Module 4 of Fluid Mechanics 2, which is a course for the second year students of Kerala Technological University. Now, let us first see what is total energy of flow. For an open channel flow, this is the datum, this is the channel bottom, this is the water surface, and this is the total energy line. So if we want to measure the total energy of flow for this open channel, let's now check the dimensions. The distance from the datum to the channel bottom is Z. The distance from the channel bottom to the water surface is Y, and the distance from the water surface to the total energy line is V squared by 2G. So adding all this up, in an open channel, the total energy of flow is given by Z plus Y plus V squared by 2G. Now, if I consider the channel bottom to be my datum, that will give me the specific energy of flow. Now, this is the channel bottom, this is the water surface, and this is the total energy line. This is the distance between channel bottom to the water surface is Y, and the distance from the water surface to the total energy line is V squared by 2G. So when the channel bottom is considered as datum, the energy of flow becomes simply Y plus V squared by 2G. You can see that from the previous slide, the term Z is missing, and this is because I have considered the channel bottom to be my datum. So the total energy is simply Y plus V squared by 2G. This is known as the specific energy of flow. That is the energy of flow when you consider the channel bottom to be the datum. It is known as specific energy of flow. Now what is important is energy curve. So what is the specific energy curve? It is a curve plotted between specific energy on the x-axis, that is Y plus V squared by 2G on the x-axis, and the depth of flow on the y-axis, which is Y. So specific energy is given by Y plus V squared by 2G. Now I'm going to split this equation. I'm going to write Y as EP and V squared by 2G as EK. Now why I'm doing this, I'll explain why I'm doing this. Here EP is equal to Y and EK is equal to V squared by 2G. Now V squared, V stands for velocity. Velocity is given by discharge divided by area, which is Q divided by By. So I've substituted V squared with Q squared by B squared Y squared. Now I have taken capital Q by capital B, discharge divided by width, as a term small q, small letter q. So small letter q is equal to capital Q by capital B. And so EK becomes equal to small q squared divided by 2G Y squared. Now I've done this because I'm going to plot a specific energy curve between the specific energy and the depth of flow. So I need all the terms in terms of the flow depth Y. Earlier, V squared by 2G was not in terms of flow depth Y. If I get it in terms of flow depth Y, it will be easier for me to plot it on a graph, and that is why I have converted V squared by 2G into Q squared divided by 2G Y squared. So now I'm going to plot this graph. Specific energy is lying on the x-axis and depth of flow Y is along the y-axis. Now how I plan to plot this, I've already split the specific energy into two terms, EP and EK. I'll plot each of them separately and add these two curves up. So this is the first curve, EP equal to Y. EP equal to Y is a straight line that passes through the origin, and that is what I've shown here. And the next curve is EK is equal to Q squared divided by 2G Y squared. Now let's see how that curve is going to come. This is the curve Ek is equal to q squared by 2gy squared. Now some of you might be having a doubt as to how this curve obtained this shape. Now I'll make it simple for you. Let's check what happens when y tends to 0. When y tends to 0, Ek tends to infinity. So when it is going closer to 0, you can see that the curve is tending to infinity. Now what happens when y tends to infinity? That is, when y tends to infinity, you can see that Ek will tend to 0. And that's what has been shown here, that Ek will tend to 0. And so we got the curve Ek is equal to q squared divided by 2gy squared and Ep equal to y. Our specific energy curve E is equal to y plus q squared by 2gy squared is a combination of the curves Ep equal to y and Ek is equal to q squared by 2gy squared. So I'm going to draw a curve that is the summation of both these curves. There, you got that. So that is the curve E is equal to Ep plus Ek that I have obtained by adding up Ep equal to y and Ek equal to q squared by 2gy squared, and that is known as your specific energy curve. So now let's take a look at the specific energy curve. Let's look at some of the features of the specific energy curve. I've just drawn the specific energy curve, and I've drawn the line Ep equal to y for reference. Now I take a value of E along the specific energy axis, that is along the x-axis. I take a value E. Now I am going to draw a line from E that goes along the curve. Now you can see that the straight line that I have drawn from E touches the specific energy curve at 2 points. The first point corresponds to a flow depth y1, and you can see that below there is one more point that is touching the specific energy curve. Let that be y2. So you can see that for one particular value of specific energy, there are two different values of flow depth, y1 and y2. This is a speciality of the specific energy curve. It's known as understanding the curve, understanding the graph. You can see that corresponding to one value of E, there are two different values of flow depth. Now there exists one particular value of specific energy corresponding to which you can get only one value of flow depth. Any value of specific energy, if you take along the specific energy curve, you usually get two different flow depths. But there is one particular point on this curve that can give you only one flow depth, and that corresponds to the minimum specific energy. You can see that specific energy cannot go below this point. That is the last point along the specific energy curve. Now corresponding to this value of specific energy, there is only one flow depth, and that flow depth is called the critical depth YC. So you can see these are some of the salient features of the specific energy curve that I'm trying to explain to you. Corresponding to one value of specific energy, there can be two different flow depths, but except for the minimum value of specific energy, which gives you only one particular flow depth, that is known as the critical depth. So let's just go through the salient features of the specific energy curve. So the specific energy curve has two limbs, one which is asymptotical to the x-axis. Asymptotical means reaches out to, but never really touches. So it is asymptotical to the x-axis, and the other limb is asymptotical to the line E equal to y. You saw the specific energy curve, that's how it is shaped. Each value of specific energy corresponds to two different values of flow depth, which means that there are two different depths of flow that have the same specific energy. So the minimum value of specific energy corresponds to just one flow depth, and this depth is known as the critical depth. So this much has been explained earlier from the graph. Now let's look at the concept of alternate depths. Alternate depths are depths corresponding to the same specific energy. So if I take the value of specific energy E corresponds to two different flow depths, y1 as well as y2. So here y1 and y2 are known as alternate depths. That is, they correspond to the same specific energy. Now let's look into detail about these alternate depths. I'm taking the specific energy curve once more. Now you have to pay a little bit of attention here because it's a graphical procedure that I'm going to explain. So if you see, I have plotted the specific energy curve and I've also plotted the line E equal to Y. The dotted line making angle of 45 degree with the X and Y axis is the line E equal to Y, and your specific energy curve has the equation E equal to Y plus V squared by 2G. So now let me consider the depth Y1. Please pay close attention to the value of depth Y1. The distance of that point till the line E equal to Y is Y1. The point that I've shown in red arrow, that value is Y1 because that point is going to lie on the line E equal to Y. So naturally, the remaining distance from the line E equal to Y to the specific energy curve should be V1 squared by 2G. Only then you get the value Y1 plus V1 squared by 2G to lie on that specific energy curve. I hope you understood what I've been trying to tell you. Y1 is the distance, the horizontal distance up to the line E equal to Y. So the remaining distance has to be V1 squared by 2G. Now let's look at the value of Y2. Now Y2, the horizontal distance shown in red, the distance, horizontal distance up to the line E equal to Y will give me the value equal to Y2. The remaining horizontal distance up to the specific energy point, the point on the specific energy curve should give me V2 squared by 2G. So you can see that V2 squared by 2G for Y2 is greater, Y2 is lesser. The value of Y2 is lesser, V2 squared by 2G is greater. Whereas for depth Y1 is the greater value, V1 squared by 2G is a small value. Now if we check the critical depth YC, you can see the red horizontal distance corresponds to the value of YC and the green horizontal distance corresponds to VC squared by 2G, where VC is the critical velocity. So based on this graph, we can make some observations. It's very important to understand these observations. You can understand that the value Y1 is greater than YC, whereas Y2 is lesser than YC. So the two alternate depths, one of them would be greater than the critical depth and one of them would be less than the critical depth. Now just like Y1 was greater than YC and YC was greater than Y2, there is an inverse relationship existing between the velocities. You can see that V2, you can see from the green horizontal line that V2 has the biggest line. So V2 is greater than VC and the smallest line is corresponding to V1. So V2 is greater than VC is greater than V1. This is an inverse relationship corresponding to the depths. So greater the depth, lesser the velocity. And so what we have understood from here is that there are two alternate depths. One of them is greater than critical depth. One of them is lesser than critical depth. The one with the value greater than critical depth has a velocity lesser than the critical velocity, and the depth with the value lesser than critical depth has a velocity greater than the critical velocity. So we'll just name these two depths. Depth Y1 corresponds to depth greater than critical depth and velocity less than critical velocity, and this is known as subcritical depth. Depth Y2 corresponds to depth lesser than critical depth and velocity greater than critical velocity, and this is known as supercritical depth. So now we'll derive an expression for critical depth. Critical depth is the depth of flow corresponding to the minimum specific energy that we have seen from the graph of the specific energy curve. So we know that the expression for specific energy is Y plus Q squared by 2GY squared. For specific energy to be minimum, dE by dy should be equal to 0. So I'm going to differentiate this expression. dE by dy is equal to 1 minus 2Q squared by 2GY cube. That's equal to 0. So solving, I'll get 1 is equal to Q squared by G y cube, or y cube is equal to q squared by g, which will give me the expression y is equal to q squared by g raised to 1 by 3. So there I have the expression for critical depth. Critical depth yc is equal to q squared by g raised to 1 by 3. This is the expression for critical depth. Now we'll find out an expression for critical velocity. Critical velocity is the velocity corresponding to the critical depth of flow. That is the velocity corresponding to critical depth. So in order to get that, I already have the expression for critical depth as yc equal to q squared by g raised to 1 by 3. So I'm going to cube it. Yc cube is equal to q squared by g. Now I know that small letter q stands for discharge per unit width, that is capital Q by B. So small q squared can be replaced by capital Q squared by B squared. Capital Q, discharge, is area into velocity, so that becomes B into Yc into Vc the whole square. Solving, I'll get Yc cube is equal to Yc squared Vc squared by G, and simplifying I'll get Yc equal to Vc squared by G. Now I'm going to find out, I wanted to find out the expression for critical velocity. So I got Vc is equal to square root of Gyc. So that becomes the value of critical velocity. Critical velocity Vc is equal to square root of Gyc. Next, we're going to find out the expression for minimum specific energy. So E is equal to y plus v squared by 2g. Now, E minimum, corresponding to E minimum, the depth of flow would be critical depth and the velocity of flow would be critical velocity. So I keep Yc as it is. Vc, I've got an expression for critical velocity as root of Gyc. So root of Gyc the whole square divided by 2g. Simplifying, I'll get E minimum is equal to Yc plus Yc by 2, or E minimum is equal to 3Yc by 2, 1.5 times the critical depth. So minimum specific energy is given by 3Yc by 2. You have to understand that here energy has been represented in terms of meters, which is energy per unit weight of water. So whatever energy that you will get it in terms of meter. The unit of energy would be in meter. Let's move on to some numerical problems. Now I want you to be clear. Please pause the video, go through the question and try to answer it on your own before going into the solution. Because it's always better that you think logically first, think yourself and find out the answer yourself, and then go through the solution. This helps you in understanding the problem and understanding the formulae much better. So let's just read through the question. Find the specific energy of flowing water through a rectangular channel of width 5 meter when the discharge and discharge is 10 meter cube per second. It's slightly misplaced, and depth of water is 3 meter. So let's go to the answer. Y, we'll go through the given data first. Y is equal to 3 meter. Q is equal to 10 meter cube per second. B is equal to 5 meter. So discharge per unit width is capital Q by B. We have got capital Q as 10 and capital B as 2. Sorry, capital B as 5, and so capital Q by B becomes equal to 2. The unit of small q, discharge per unit width, would be meter squared per second. Now we have been asked to find out the specific energy. The formula for specific energy is y plus q squared by 2gy squared. Simply substitute and you will end up getting the answer to be equal to 3.0226 meter. Let's go to the next question. Find the critical depth and critical velocity of water flowing through a rectangular channel of width 5 meter when the discharge is 15 meter cube per second. Again, we have ready-made formulae for critical depth and critical velocity. The width of the channel is given, the discharge is given. All you need to do is find out the value of small q, substitute to find out the value of critical depth. Once you get the critical depth, you can simply find out the critical velocity. You can pause the video, work out this problem, and then go and check the solution. This is the solution. Capital Q is equal to 15 meter cube per second. Capital B is 5 meter. Small q is equal to 3 meter squared per second depending on the calculation. The formula for critical depth is Q squared by G raised to 1 by 3. Substituting, I'll get the value as 0.972 meter. Critical velocity is root of G by C. YC has already been found out. Substituting, critical velocity becomes 3.088 meter per second. This is supposed to be question 4. Specific energy of 5 meter wide rectangular channel is 4 meter. If the rate of flow through the channel is 20 meter cube per second, determine the alternate depths of flow. So here, you've been asked to find out, we all know that corresponding to one value of specific energy, there are two different flow depths corresponding to the same value of specific energy. And so, they've given that the value of specific energy is 4 meter, and they've given the width of the channel to be 5 meter. The discharge is given, so small q can be found out. Now, you can find out the alternate depths of flow. How do you find this out? E, the formula for E is y plus q squared by 2gy squared. Your y is unknown. You end up getting a cubic equation in y, which can be solved. So let's go through the answer. Q is 20 meter cube per second. B is 5 meter, which means small q, you will get it as 4 meters squared per second. The specific energy has been given to you. Given that specific energy is 4 meter. So y plus q squared by 2gy squared is 4. I'll substitute the values that I know already. I know that small q is 4. 2 into g is 19.62. Simplifying, I will get this expression and rearrange it to get a cubic equation. This equation can be solved, and on solving, we will get the values of y to be 3.95, negative 0.42 and 0.48. So discarding the negative answer, we will get the value of alternate depths of flow as 3.93 meter and 0.48 meter. I think the slide was slightly misplaced. Question 3 is coming up now, but that doesn't matter. Now go through the question number 3. The discharge of water through a rectangular channel of width 8 meter is 15 meter cube per second, when the depth of flow is 1.2 meter. Calculate the specific energy of the flowing water, the critical depth and the critical velocity, and the minimum specific energy. So you can use all the formulae that you've studied till now. You can work this problem, pause the video, work out this problem, check the solution later on. Let's go to the answer. The depth of flow is 1.2 meter. Discharge is 15 meter cube per second. Width of flow is 8 meter. So discharge per unit width comes to 15 divided by 8, which is 1.875 meters squared per second. Specific energy is given by y plus q squared by 2gy squared, which is 1.2 plus 1.875 squared divided by 2 into 9.81 into 1.2 squared. I simply substituted the values that are already known to me, and I got the value of specific energy, which was the first part of the question. Second part of the question asked me to find out the critical depth and critical velocity. Both of the terms, I know the formula. Critical depth is q squared by g raised to 1 by 3. Data is available with us. So YC comes to 0.71 meter. Now you need to know YC to calculate the critical velocity. Critical velocity formula is root of GYC. I end up getting the answer to be 2.639 meter per second. And finally, the value of minimum specific energy. We all know that the value of minimum specific energy was 1.5 times the critical depth. So E minimum comes to 1.065 meter. And that is the numerical problem. Another numerical problem on the same topic. You can see that all these numericals are very simple, direct substitution problems. Once you know the concept, you will understand it easily. But the thing is that more than numerical problems, the type of questions that are going to come from this topic are going to be based on your specific energy curve. To plot the specific energy curve, to discuss its salient features, to discuss about alternate depths is what is going to come for high marks. So you have to be very clear on the concept of specific energy. Now let's discuss what is meant by the FROUDE number. The FROUDE number is a dimensionless number that is significant in open channel flow. So what is Froude number? It's given by velocity divided by root of gy. This is how Froude number is defined. Velocity divided by root of gy. So for critical flow, Froude number would be critical velocity divided by root of g into yc. But for critical flow, we know that critical velocity is root of g yc, which means that Froude number for critical flow is equal to 1. This is very important. Froude number for critical flow is equal to 1. Let's just check the Froude number for subcritical and supercritical flow as well. For subcritical flow, V1 is less than Vc and Y1 is greater than Yc. And so, Froude number Fr, which is V1 by root Gy1, would be a value that is lesser than Vc by root of Gyc. And so, for subcritical flow, Froude number is a value less than 1. You take the case of supercritical flow, V2 is greater than Vc and Y2 is less than Yc. And so the Froude number V2 by root Gy2 is greater than Vc by root Gyc. Hence, for supercritical flow, Froude number is greater than 1. So you can see that Froude number is a number, a dimensionless number that is used to differentiate between critical, subcritical and supercritical flows. We all know about Reynolds number that is going to differentiate between, that is helping us to differentiate between laminar and turbulent flow. Similarly, Froude number helps us differentiate between critical, subcritical and supercritical flow. If Froude number is equal to 1, flow is critical. If Froude number is less than 1, flow is subcritical. If Froude number is greater than 1, flow is supercritical. So these are some self-assessment questions, all simple ones, and correspondingly we have done some similar questions in our slides before this. So what you can do is, you can work this out. It won't take you more than half an hour to work out all the problems. It's very simple. And you have to also practice the specific energy curve, how it is plotted, what are the values, how alternate depths are arrived at, and what are the salient features. Now I have given a slide on salient features. That are not the only salient features of specific energy curve. You must also mention about the alternate depths and how the Y1 and Y2 are related to IC and V1 and V2 are related to VC, because all that will be included in the salient points of a specific energy curve. So I hope this topic was an easy topic and I hope that you have understood it.